Today we learn about how to identify whether a given function is a 1-1 function or whether it is an onto function. Okay, if they can also ask you whether to justify whether a function is many one. So obviously if you see that it does not satisfy the 1-1 criteria, then it has to be a many one function. Similarly, they can also ask you to identify whether a given function is into function or not. So in that case, you will check whether it is onto. If it doesn't satisfy the onto criteria, then the conclusion will be therefore it must be an into function. So the main thing is we will learn how to identify a 1-1 function and how to identify a onto function. 1-1 function means what? For every x you will get a single value of y and vice versa, that is for every y you will get a single value of x. So the logic behind this that is used is, if I assume that fx1 is equal to fx2 for any values of x1 x2, that means the y values are the same in the set the b that is given, that is the function is from a to b, then obviously we will have to it has to lead to that x1 is equal to x2. That means there is only one value of x for which we can have only one value of y. Okay, x1 equal to x2 means what? There is a single value of x. If I am assuming that there are two values of y for two different values of x, and if I am getting that the x values are the same, that means it will mean that this function is 1-1. Excuse me. Okay, so that means the x values are the one and only one unique x values we are getting. So for every x we are getting a unique y. This is equal to this means y. What? These are values of y which are equal. That means this is a unique y in itself. So if I assume that two y values for two given x values are the same, and then it is leading to the fact that the two values are also the same, it means a unique value of y corresponds to a unique value of x. So obviously a unique value of x corresponds to a unique value of y. So therefore it is a 1-1 function. Next, how will you identify an onto function? Very simple. You will assume that there is a y which is belonging to the codomain, and you will show that there exists an x which belongs to the domain which satisfies the equation fx is equal to y. If you don't get such a value of x, okay, that is if you get a value of x which does not belong to the domain, then obviously that x value does not exist, or you can say that pre-image of y does not exist in the domain. In that case it cannot be a onto function. Okay, it will be an into function, because that is actually the leftover in the second set. If you remember what is an onto and what is an into function, especially the diagrams, then you will be able to identify. So this is the principle behind identifying an onto function. That is, if you remember, for an onto function, range is equal to codomain, isn't it? So that means there should not be any value of y which does not have any value of x in the domain. So if I get such a situation where there is no value of x belonging to the domain, or if I get a value of x from this solving this equation which does not belong to the domain, then my conclusion will be it is not an onto function. Okay, otherwise my aim will be to find the value of x which belongs to this domain and which corresponds to the solution of this equation fx is equal to y, because that x is going to be the pre-image of y. So therefore these are the ways of identifying a 1-1 function and an onto function. Let's move on to an example. The question says, prove that the function f from q to q. Q to q means from rational numbers to rational numbers. That means the domain is also a rational number, the codomain is also a rational number. Given by fx is equal to 2x plus 3 for all x belonging to q is a bijection. Bijection means what? If you remember, it is 1-1 and it is onto. That is what you have to show. So first we will show that it is 1-1. That is the first part. How will we show? We are assuming that let fx1 is equal to fx2 for any x1, x2 value belonging to the domain q. Okay, now what does it mean? According to the question, fx is what? 2x minus 3. So fx1 will be 2x1 minus 3, fx2 will be 2x2 minus 3. So this 3 and 3 cancels, and therefore you are left with 2x1 is equal to 2x2, and therefore x1 is equal to x2. So you can see, when I assume that fx1 is equal to fx2, it has led to x1 is equal to x2. Therefore it satisfies the criteria that we discussed earlier. So therefore fx is a 1 function. Similarly, let us assume, now we will show that it is an onto function. We will begin with let y belong to b. B means the codomain. Here codomain and domain both are same. So we will mention that we are taking the codomain. So let y belongs to q, the codomain, which satisfies the equation that fx is equal to y. Okay, let us solve this. We will have to find the value of x. So 2x minus 3 is equal to y. So x is equal to y plus 3 by 2. Now y plus 3 by 2 is definitely a rational number. So we are stating that which is definitely a rational number. That means x belongs to q. In other words, x, which is this, belongs to the domain q. So for an arbitrary value of y which belongs to the codomain, we are getting a value of x which belongs to the domain. Hence, this function must be an onto function. Final conclusion, combining these two results, we have that the function fx is a bijection. Okay, we move on to next one. Show that the function f from R to R, that is from real numbers to real numbers, defined by fx is equal to 3x cubed plus 5 for all x belonging to R is a bijection. So again we will show that it is 1 onto. We will assume that let fx1 is equal to fx2. Put what is fx1? Here it will become fx1 means in place of x you are putting x1 and the expression value that you get. So it's 3x1 cube plus 5 on this side, and that side it is 3x2 cube plus 5. So 5 and 5 cancels. So it's x1 cube is equal to x2 cube, which implies x1 is equal to x2. It's not x1 is equal to plus minus x2, because minus x2 whole cube would have been minus, and here both sides it is positive. So this means both have to be positive. So x1 is equal to x2. So hence what have we obtained? Starting from fx1 is equal to fx2, we obtained x1 is equal to x2 for any x1, x2 values which belongs to the domain R. Yes, so therefore fx is an injection, or we can say fx is an injective function or a 1 function. Then we will move on to showing it is onto. Let y belong to the codomain. We'll mention, we are writing y belongs to R, but mention that you are taking R from the codomain. Okay, so let y belongs to the codomain, and this means it satisfies the equation fx is equal to y. So this means 3x cube plus 5 has to be y, from where we will make x as the subject. This is your x cube, and this means x is y minus 5 to the power 1/3, which has to be a real number. That means this x belongs to the domain. So conclusion that is that for any y which belongs to the codomain, there exists an x which belongs to the domain. Okay, and which is given by, you can write this if you want, this step is optional. Okay, I've written it explicitly. What is fx? Fx, we are checking actually, fx is giving me this, I'm putting in place of x this expression, automatically I'm getting y. This is just a cross check, it's not necessary that you have to do it. You can straight away after this you can write, therefore every element of the codomain has its pre-image in the, and since y is arbitrary, isn't it, for any arbitrary y you are getting a value of x. So therefore it means every value of y that you take in the codomain will correspond to a value of x which will correspond to a value of x which is a real number in the domain. So that is why every element of the codomain has its pre-image in the domain. You can mention this line if you want, otherwise straight away you write, therefore fx is a surjection, or it is a surjective function, that is it is an onto function. And final conclusion, hence fx is a bijection, or it is a bijective function. Moving on to the next question, we have a set A given by R minus 2. What does it mean? Moving on to the next question, A is a set R minus 2. What does it mean? It is the set of real numbers excluding the element 2. Okay. B is the set R minus 1. It is the set of real numbers excluding the element 1. F is a mapping from A to B, okay, which is defined by fx is equal to x minus 1 by x minus 2. You have to show that it is bijective, okay. So I wrote it like this. F is from A to B, so I wrote it more explicitly. What is it actually? F is R minus 2 replacing A, to R minus 1 replacing B, okay. And then I will follow whether it satisfies the definition or not. What is the definition? Let x1, x2 belong to the domain. This is your domain. This is the set A, which is R minus 2, such that it satisfies fx1 is equal to fx2. We will see whether it gives me x1 is equal to x2 or not. So I'm putting fx1. What should it be? Substitute here x1 minus 1 by x1 minus 2 equal to x2 minus 1 by x2 minus 2. Okay, so cross multiplying x1 minus 1 into x2 minus 2 is equal to x2 minus 1 into x1 minus 2, and then you multiply, you will see some of the terms getting cancelled. So it's minus 2x1 minus x2 minus 2x2 minus x1. So minus is common, you can get rid of it from both sides, or you can do one thing, you can rearrange. That is, you have x2 over here and you have minus 2x2 over here. Bring minus 2x to this side, so it becomes 2x2 minus x2, and bring this minus 2x1 that side, so it's becoming 2x1 minus x1. That is, we are transposing. So this is what I have. Therefore, it is simply x2 is equal to x1, which is the same as x1 is equal to x2. So thus, starting from fx1 is equal to fx2, we obtained x1 is equal to x2. So it means that f is a 1-1 mapping. Okay, then we will do for onto. How will we proceed? Let y belong to the set B, which is R minus of 1, this one, this set, which is an arbitrary element in B. So it satisfies the condition fx is equal to y. If it does, then this is the situation. That is, I have replaced fx by this, and then I will simplify this and make x as the subject. So simplifying, you know how to simplify, nothing much to explain. X minus 1 is equal to yx minus 2y. That is what here. These two contain x, so bringing them to one side. X common, 1 minus y is equal to 1 plus 2y, as a 1 minus 2y. So therefore x is 1 minus 2y by 1 minus y. So we have to check whether this x belongs to the domain set or not. Okay, and the question is, clearly x minus this value definitely is a real number, no doubt about that, provided y is not becoming 1, isn't it? If y becomes 1, then this will no longer exist, because it's going to become undefined over here. So so that is what I've written. Clearly x is equal to this belongs to R, provided y is not equal to 1. And definitely y is not equal to 1, because we have seen that y belongs to the codomain. Y belongs to the codomain, and therefore which does not include the element 1. So obviously y will not have the value 1. Okay, this codomain does not have the element 1. So y, which I choose from here, which is supposed to be an element from here, will definitely not be 1. Okay, so therefore that is what I have written. This will belong to R, that is real numbers, provided y does not. This will be a real number provided y is not 1. And definitely this is true, because this is given by definition. Okay, we have seen in the codomain. So therefore, and not only that, we see that x is not equal to 2 also, because if x had been equal to 2, what would happen? 1 minus, replacing x now, I am cross checking actually, 1 minus 2y by 1 minus y, which we got in the previous step, is 2. Cross multiplying, we get 1 is equal to 2, which is not at all possible, which is something very absurd if x is equal to 2. So therefore definitely x is not equal to 2. So what is our conclusion? Thus for y belonging to B, B is what? B is the second set R minus 1. You can write over here, thus for y belonging to B, which is R minus the element 1, that is set of elements excluding 1. This symbol is there exists, inverted E. Okay, there exists an x belonging to R minus of A, that is R minus 2. Okay, So definitely this is not clear, I think. R minus 2. So definitely every element of y in B has a preimage in A, which is given by this. So I can say that F is a surjective mapping. So combining these two results, I have F is a bijection. Okay. In fact, this function that you get x is equal to this is actually representing the inverse function, isn't it? Because recall the definition, I've written here it as a note, that if y is equal to fx, from there I get x is equal to function of y, which since I've obtained from this, instead of using gy, I will use the symbol f inverse, showing the fact that this is the inverse function obtained from this, where now x is the dependent variable, y is the independent variable. The expression that I have is such that x is dependent, y is now independent. So thus, for a given mapping, thus the inverse mapping, which is f inverse, is from B to A, and it is, in this particular case, it is given by f inverse y, which is the expression for x, that is, where is it here, 1 minus 2y by 1 minus y. Okay, so you can write this as a conclusion if they ask in the question. Here they did not ask, but they can ask you what is the inverse function. But generally I think according to reduced syllabus you don't have to find inverse function. But when the moment you are showing that it is an onto function, you are automatically actually obtaining the inverse function, isn't it? Even if they don't ask, you are actually obtaining it. So you can add on to that this is the inverse function, otherwise you can leave it as it is. Okay, the next question now. Show that the function f given by r minus of minus 1 to r minus of 1, that means what? Set of real numbers excluding the element minus 1, and this is set of real numbers excluding the element 1, which is given by fx is equal to x by x plus 1 is invertible. And also find the inverse function. This they may not ask, whatever. Show that it is invertible means you have to show that it is a bijection, because remember in the last class we stated that if and only if a function is bijective, then only it will have its inverse function. Okay, or that it is invertible. In fact, that is what I've written also. Recall, a function has its inverse, that is, it is invertible if and only if it is a bijection. So we basically have to show over here that f is a bijective function, or f is a bijection over here. So first step is we will show that f is 1, 1. Okay, how will we show? That is, we will show that f is 1, 1. So we will assume that let x1, x2 belong to the domain set, which is r minus of minus 1, such that it satisfies the equation fx1 is equal to fx2. We will solve this now, that is, we are substituting fx is what? X by x plus 1. So fx1 will be x1 by x1 plus 1. So x1 by x1 plus 1 is equal to x2 by x2 plus 1. So we will simplify this now, cross multiplying. x1 x2 plus x1 is equal to x1 x2 plus x2. x1 x2 cancels. You are left with x1 is equal to x2. So what have we obtained? Thus fx1 is equal to fx2 gives us x1 is equal to x2. Hence f is a 1, 1 function. Now we will show that f is onto. We will take an element from the codomain now. Codomain is what? This one, r minus of 1. So we will take an element, say y, which is arbitrary, from the codomain r minus 1, which satisfies the equation fx is equal to y. So we will solve this to get x. So fx is this, simplifying, that is cross multiplying, x common over here, 1 minus y is your y, so x is equal to y by 1 minus y. So this value of x is a real number and it will exist provided 1 minus y is not 0, that is the denominator is not 0. In other words, provided y is not equal to 1. Okay, and definitely y is not equal to 1. Why? Because in the codomain that is given, the set which we are saying is the codomain does not contain 1 according to the given question. So definitely this x will exist. Okay, because y is never 1, y can never take up the value 1. So this x will exist and it is a real number, but we have to check whether x is minus 1 or not, because x should not be minus 1, because minus 1 does not belong to the this one, domain. Okay, so that has to be checked. So clearly we are writing that clearly x belongs to R provided 1 minus y not equal to 0, that is denominator not equal to 0, what I said verbally. So therefore y is not equal to 1, and which is true because y belongs to R minus 1. So definitely x belongs to R. Now we will check in order that x belongs to A. Now x has to belong to A, isn't it? The domain. When will it belong to A? If the domain is what? Domain set is the set of real numbers which does not contain minus 1. So we have to make sure that x does not take up the value minus 1, because if x takes up the value of minus 1, then it cannot belong to this domain, because this domain does not contain minus 1. So we are checking that, as we did in the last sum also, that we are doing by contradiction now. Okay, contradiction, that is what I've written first. In order that x belongs to A means the domain set, that is R minus of minus 1, it is necessary that x should not be equal to 1. Why? Because domain does not contain this element minus 1. I've written in words. We are doing by contradiction. If possible, there also we did, because if x is equal to 2, that means actually we are assuming that if x is equal to 2, then what would happen? So here also we are doing that if x is minus 1, then what would happen? It would give me y by 1 minus y is equal to minus 1. So y is equal to minus 1 plus y. So it gives me an absurd result, that is 0 is equal to minus 1. So definitely if x is equal to minus 1, then it is giving me absurd result. So definitely x cannot be equal to minus 1. So that is my conclusion. Hence x is equal to minus 1 is not possible. That is, x is not equal to minus 1, which means that x belongs to R minus of minus 1, that is the domain. And therefore, what is your conclusion? I've written, of course, in the next step. Therefore, x belongs to this. Anyway, I've written it twice. Forget it. Thus, for every y belonging to R minus 1, there exists a pre-image x belonging to the domain R minus of minus 1. And therefore, f is onto. So combining these two, this first subpart and the second subpart, I can say that f is a bijection, and consequently it is invertible, or it has an inverse function. What is the inverse function? This is the inverse function. X is equal to y by 1 minus y, and how will we represent it? We will represent it by writing f inverse y is equal to y by 1 minus y. That is what I've written here. F inverse is the mapping from B to A, so it will be from this to this. So it is a mapping from R minus 1 to R minus of minus 1, which satisfies the expression that we cannot write f now, we have to write f inverse, and since it is an expression in y, so we are writing f inverse y is equal to y by 1 minus y. Okay, so just like we have fx is equal to this, when we are writing the right hand side as an expression in x, the left hand side has to be fx. So here also, when right hand side is in terms of y, left hand side has to be in terms of y. We are using the symbol f inverse, showing that it is the inverse function of the given function. So in general, we can generalize this and write also, that is f inverse is y by 1 minus y. So this is what we have under inverse, or rather what we have under mapping, where you have to show that a given function is 1, 1 and it is onto. Okay. Next we have something called composition of functions. Okay, this is a very simple thing, but then this year it has been included in your syllabus, so we have to do it. So composition of functions means, what does it mean? F is a function from A to B, G is a function from this B, okay, observe, from this B to another set C. Okay, so if I draw it, suppose this is a set A, this is a set B, this is a set C. This is a mapping F from A to B, this is a mapping from B to C. I've written G over here. Then G compose F. This circle over here is read as compose. Okay, so G compose F means it is the mapping from A to C. Okay, even though we are writing G compose F, but it is a mapping from A to C. Mind you, I hope you have noticed that. So F is a mapping from A to B, G is a mapping from B to C. So G rho F that is G compose F, second one compose F will be a mapping from A to C. Now why G compose F? Because this actually means G compose F of X. Okay, I wrote it in short. G compose F means actually it is G compose F of X. It's like this. It is given by G compose F of X, which means G of Fx. What is the meaning? It is G of Fx. Okay, for all X belonging to the first set, that is the domain of the starting point. And this function G compose F is called the composition of the two functions F and G. And the question is, what is the meaning of this and how will we apply it? Let's take up an example. F is a function from real numbers to real numbers given by fx is equal to x square, and G is a function from real numbers to real numbers given by gx is equal to 2x plus 1. You have been asked to show that F compose G is not equal to G compose F. We start from the left hand side. F compose G means actually F compose G on X, where X is a element of the domain set. This means F of Gx according to this definition. Okay, I didn't write that. This means F of Gx. Now F of Gx means what? Gx, we have an expression. Let us replace it. So it means F of 2x plus 1. Now F of anything, this is your fx. F of 1 means what? 1 square. F of 2 means what? 2 square. So F of 2x plus 1 means what? In place of x, you will replace by 2x plus 1. If it had been f of x square, it would mean you have to replace x by x square. It will become therefore x square whole square. If it had been f of x cube, then it would mean that in place of x, you are replacing x cube. So it's becoming x cube whole square, that is x to the power 6. Okay, like that. So f of 2x plus 1 means you are replacing x by 2x plus 1. So it is nothing but 2x plus 1 whole square. Now let us find out what is G row F. Now G compose F. G compose F of X. What does it mean? It means G of Fx. G of Fx means, let us replace Fx. Fx is x square, so it's G of x square. Now G is this. G of x square means wherever you have x, you have to replace by x square. So G of x square means this is becoming 2 of x square plus 1. So what can we observe? This is F row G and this is G row F. Are they same? No, they are not the same. Hence conclusion, F row G is F compose G is not equal to G compose F. Okay, so that was something in general. If we have finite sets, another example, let us move on to F is a function from the elements 2, 3, 4, 5 to the elements 3, 4, 5, 9. Okay, and G is a function from the elements, this one, that is 3, 4, 5, 9 to another set whose elements are 7, 11 and 15. You can separate them. You can write this as A, this as B and this as C. So separately to make it look neat, and you can write that F is a mapping from A to B, G is a mapping from B to C. And it is such that f of 2 is 3, that means functional value of 2 is 3, that means this is related to this. Okay, f of 4 is 5, f of 4 is 5, that is this is related to this. F of 3 is 4, f of 3 is 4, and f of what else is given? Nothing else is given. So f of 5 is actually not given. No, it's given. F of 5 is also 5. Okay, so this is the extra term over here. 9 is not related to anything, isn't it? 3, 4, 5 is there in the codomain of the first function, but 9 is not used. Anyway, G, what else is given? G3 is and G4 is 7. So 3 is associated with 7. 4 is also associated with 7. Okay, G5 and G9 is 11. So this 5 is associated with 11. 9 is also associated with 11. So 15 is left over. Here 9 is left over in the codomain, and here 15 is left over in the codomain. Anyway, we'll see to that. So I've written it more explicitly. They have asked you to find G compose F. How will you find? First I'm labeling this as set A, 2, 3, 4, 5. I'm labeling this as set B, and I'm labeling this as set C. So what is the mapping F? It is from A to B, and G is the mapping from B to C. We have to find the mapping G compose F, which is from A to C. That means we have to choose elements of A, each and every element, mind you, because a function, if you remember, every element of the domain. This is a function basically, isn't it? Every element of the domain has to be assigned to a unique value of the codomain. Okay, so we have to choose elements of the set A such that they give me elements of set C. So what is G rho F? Let us choose elements of set A. First element is 2. So G compose F of 2, what is it? Let me see. G compose F of 2 means G of F2. Okay, it means G F2 value is given. F2 value is, I think, 3. So we are putting 3 over here. So we are getting G of 3, and G3 is also given as 7. So we are writing that. That means what? G rho F mapping is mapping the element 2 to the element 7. Okay, then G rho F of the next element in A, that is 3. Here you have A, sorry, 3. So it means G of F of 3. F of 3 value is given over here as 4. We put it over here, so it becomes G of 4. G4 is given over here as 7. So the value is 7. Similarly, G compose F on the next element of A, that is 4. So it is G of F4 by definition, and F4 is given as 5. So therefore it's G of 5, and therefore it is 11. Okay, so this is what we have. G compose F of 5. G compose F of 5 means it is G of F5. Okay, by definition, F5 is given as 5. So we put 5 over here. It's becoming G of 5, and according to question, G5 is 11. Okay, so what are the pairs that we are getting? 2 is assigned to 7, 3 is assigned to 7, 4 is assigned to 11, 5 is assigned to 11. Okay, so this is a mapping from 2, 3, 4, 5. Okay, 2, 3, 4, 5, that is the set A, to the elements 7 and 11. So that is what we have written. G compose F is a mapping from, to just the way that they have written, we have written it like that. 2, 3, 4, 5 to 7 and 11. But then C is having 7, 11 and 15, isn't it? So therefore 7, 11 and 15 has to be written. But what is the definition of G rho F is what that is what they want. And what is, how do we define it? We cannot have any formula as such, because there's no perfect expression over here given. So we will write it in terms of ordered pairs. Okay, so we will write it as 2, 7, that what we got, 2, 7, 3, 7, 4, 11, 5, 11. So G compose F is given by this ordered pairs, because we cannot write it in the form of any expression. If we could have written it in the form of an expression, and that would be possible if and only if the expression for F and the expression for G would have been given, but it's not given over here, so we have to write it like this. G rho F is a mapping from A to C. A is given over here, C is given over here. And how is it defined? That 2 is associated with 7, 3 is associated with 11. Is it? Did I say correctly? No, 3 is associated with 7, 4 is associated with 11, and 5 is associated with 11. The element 15 is redundant. It is left as it is. Doesn't matter. It's actually a into mapping. It's into function. Okay. One more thing you need to know, G compose F will exist if and only if the range of F is a subset of the domain of G. Okay, and this can be a small question of 1 mark maybe. Similarly, F compose G will be existing if range of G will be a subset of domain of F. This is obvious. This I don't think it needs any explanation, but please remember it. Okay, range of F is what? Range of F in this particular case, range of F, what is this? This is your domain, this is your codomain. So what we get from here, in this case, what is the range of F? Range of F is actually 2, 3, 4, 5. 2, 3, 4, 5 is assigned to 3, 4, 5. So range is actually 3, 4, 5. Codomain is 3, 4, 5, 9. Okay, so this range has this range of F has to be a domain of a subset of the domain, obviously, because actually codomain of F is codomain of G, isn't it? Codomain of F is domain of G, sorry. Yes, please note here also in the definition itself, the codomain of F is the domain of G. So definitely Here also, if you observe the example, codomain of F is the domain of G. So the range of F will definitely be a subset of the codomain, and therefore range of F will be a subset of the domain of G. Okay, so that is the logic behind this. Similarly for F row G. F row G will be the other way around. F row G will be a mapping from the C to this one. What do you call it? C. Where is it? 0F will F row G will exist if and only if range of G is contained in the domain of F. Same logic. Okay, but please remember. In fact, nothing to remember. If you understand, you can remember it easily. Okay. The next example now, f of 3, f is a function from R to R given by fx is equal to x square plus 2. G is a function from R to R given by gx is equal to x by x minus 1. You've been asked to find whether f compose G is the same as G compose f. F compose G of x means what? By definition, f of gx. So it's f of, replace gx, this is x by x minus 1. So it's f of x by x minus 1. So wherever in place of x, you will put x by x minus 1. So this is becoming x by x minus 1 whole square plus 2. Similarly, G compose f, it is G of fx. Okay, so this means G of fx. What is fx? X square plus 2. So it's G of x square plus 2. That means wherever you have x in G, you will put x square plus 2. So this is becoming x square plus 2. This is x square plus 2 minus 1. So it's x square plus 2 by x square plus 1. What is your conclusion? Even if you simplify this, you will never get this. So therefore, conclusion, you can check and see whether you are getting or not. Definitely you will not get this. So your conclusion is F compose G is not equal to G compose F. Okay, so this is what we have. That's all about composition of functions.